Hello! In today's video, we're going to dive into some fundamental concepts in mathematics. By the end of this session, you will be able to distinguish between rational and irrational numbers, understand how to compare numbers using inequalities, and master the concept of absolute value. Our main topics will be irrational numbers, inequalities in real numbers, and the absolute value of a real number. First up, let's talk about irrational numbers. You've probably already heard of some. A widely known example is pi. Pi appears in countless formulas for calculating the circumference, area, and volume of circular shapes, making it a very special number. But what exactly is an irrational number? There are two key properties that define them. First, an irrational number is a number that can be written as a non-terminating and non-repeating decimal. This means the decimal part goes on forever without ever settling into a pattern. Second, and this is a consequence of the first point, an irrational number cannot be expressed as a fraction a over b, where a and b are integers and b is not zero. You can't write it as a simple ratio. It's a common misconception that all square roots are irrational. Let's test that idea. Consider the square root of 4. This simplifies perfectly to 2. We can write 2 as the fraction 2 over 1. So, the square root of 4 is a rational number. Now let's look at the square root of 2. If you type it into a calculator, you get a number like 1.41421356 and so on. The decimal part never ends and never repeats. You also can't write the square root of 2 as a simple fraction. Therefore, the square root of 2 is in fact an irrational number. So, a good rule of thumb is, if you take the square root of a number that is not a perfect square, you will get an irrational number. This is an important distinction to remember. Let's look at some examples of irrational numbers you might encounter. This will help solidify your understanding. The square root of 2, as we just saw, is approximately 1.4142. It's non-terminating and non-repeating. A number you might see in more advanced math is Euler's number, or A. It's about 2.71828. Like pi, it's a fundamental constant in calculus and other fields. And of course, there's pi, which is about 3.14159. Pi is a perfect example of an irrational number. You can also have negative irrational numbers like the negative square root of 5, which is roughly negative 2.236. Similarly, the square root of 11 is another irrational number. It's approximately 3.316. And the negative square root of 21, approximately negative 4.582, is also irrational. In all these examples, you can observe that the digits after the decimal point continue infinitely without repeating. This is the defining characteristic of an irrational number. They are also referred to as transcendentals. Now, let's practice identifying them. We'll take a list of numbers and pick out all the irrational ones. Here is our list. We need to go through each number and decide if it meets the criteria for an irrational number. Let's analyze them one by one. Let's start with the easy ones. Negative 6 is a rational number. So is 8.47, which is a terminating decimal. Pi is one we already know is irrational. But what about the square root of 8? To check the square root of 8, we look at 8. It's not a perfect square. When we calculate its value, we get 2.828. 427, which is non-repeating and non-terminating. This means it cannot be written as a fraction. So, the square root of 8 is an irrational number. This leaves us with two irrational numbers in our list, pi and the square root of 8. This example shows the importance of simplifying and evaluating each number. Always be cautious when you see a square root, as it might or might not be irrational, depending on the number inside. Now, let's look at how irrational numbers fit into the bigger picture of real numbers. Real numbers encompass both rational and irrational numbers. We can visualize this relationship using a diagram. Imagine a large oval that represents the set of all real numbers. Inside that oval, there are two distinct non-overlapping sets. One side contains all the rational numbers, and the other side contains all the irrational numbers. Remember, no number can be both rational and irrational. Within the rational numbers, we have a smaller group called integers. These are whole numbers and their negative counterparts. And inside integers, we have whole numbers, which are non-negative integers. Finally, the smallest set is natural numbers, which are positive whole numbers. This hierarchy shows how all these different types of numbers are related. It's also important to remember two key properties of real numbers. First, every single real number corresponds to exactly one point on a number line. And second, the reverse is also true. Every point on a number line corresponds to a unique real number. This one-to-one relationship is why we use number lines so often. Next, let's explore inequalities. In mathematics, an inequality is a statement that compares two values or expressions that are not necessarily equal. Inequalities are all around us in real life. For instance, a speed limit on a road means your speed must be less than or equal to a certain value. Similarly, event organizers might set a maximum number of attendees, so the number of guests must be less than or equal to that limit. Even in school, you need to achieve a minimum pass mark to receive a certificate, meaning your score must be greater than or equal to that mark. These are all examples of inequalities. To work with them mathematically, we use special symbols. The less than symbol points to the left, indicating that the value on the left is smaller. The greater than symbol points to the right, showing that the value on the left is larger. When we include equality, we add a line underneath the symbol. So, less than or equal to means a number is either smaller or equal, and greater than or equal to means it's either larger or equal. Understanding these symbols is the first step to working with inequalities. Let's use a number line to compare two real numbers. The rule is simple. A number to the right of another number is always greater than it. So, let's take two decimals, 0.54 and 0.33. We want to compare them. First, we represent them on a number line. They both lie between 0 and 1. When we place them on the line, we can see that 0.33 is to the left of 0.54. Because 0.33 is on the left, it is the smaller number. Therefore, we can write that 0.33 is less than 0.54, or, equivalently, 0.54 is greater than 0.33. This seems straightforward for positive numbers, but it's especially helpful with negative numbers. Let's compare negative 0.54 and negative 0.33. Again, we place them on a number line, this time between -1 and 0. Notice that negative 0.33 is to the right of negative 0.54. This can feel counterintuitive, but the further a number is to the right, the greater it is. So, negative 0.33 is greater than negative 0.54. This example highlights why visualizing on a number line can prevent common errors. Number lines aren't just for comparing two numbers, they're also essential for representing the solution sets of inequalities. Suppose we have the inequality x is greater than 1/2. We need to show all real numbers that are greater than 1/2 on a number line. This inequality means that 1/2 itself is not part of the solution. When a number is not included, we represent it with an open circle. So we place an open circle at 1/2 on the number line. Since x is greater than 1/2, all the numbers that work are to the right of 1/2. We draw a bold line extending from our open circle to the right, with an arrow at the end to show it goes on forever. Now, what if the inequality includes the number itself? Consider the inequality negative 1/2 is less than or equal to x, and x is less than 2. This is a compound inequality. Let's break it down. For negative 1/2 is less than or equal to x, the number negative 1/2 is included. When a number is included, we represent it with a closed, or filled, circle. So we draw a filled circle at negative 1/2. The second part, x is less than 2, means 2 is not included. So, we draw an open circle at 2. Finally, we connect the filled circle at negative 1/2 to the open circle at 2, with a bold line. This segment represents all the real numbers that satisfy our compound inequality. We focused on inequalities for all real numbers. Now, let's see how this changes when x is specified as an integer. Let's locate the integers for which negative 1 is less than x, and x is less than 4. Because x must be an integer, we are looking for whole numbers only. We start with a number line. The inequality states that x must be strictly greater than -1. The first integer greater than -1 is 0. The inequality also states that x must be strictly less than 4. The last integer less than 4 is 3. So our solution is the set of integers 0, 1, 2, and 3. On a number line, we represent integers with solid black dots. We place dots at 0, 1, 2, and 3. We do not connect them with a line because we are only including the specific integers, not the numbers in between them. This is the key difference between representing real numbers and integers. Let's try another one with integers. This time we have a non-strict inequality. X is greater than or equal to -2 and less than or equal to 6. Since x is greater than or equal to -2, the first integer is -2. And since x is less than or equal to 6, the last integer is 6. Our solution set is the sequence of integers from -2 to +6, inclusive. We show this on the number line, with solid dots placed at every integer from -2 all the way to 6. This visual representation makes the solution set clear. Our final topic is the absolute value of a real number. You can think of absolute value as representing distance on a number line. Formally, the absolute value of a real number x, denoted by vertical bars around it, is its non-negative value regardless of its sign. For example, the absolute value of 2 is 2. The absolute value of -2 is also 2. Both 2 and -2 are exactly 2 units away from 0 on the number line. Let's formalize this. The absolute value of x is x if x is greater than or equal to 0. But if x is less than 0, its absolute value is -x. This negative sign might seem strange, but it's there to make the result positive. For example, if x is -2, then -x is -2, which is +2. The result is always positive, because distance is always positive or 0. Let's evaluate a few expressions. The absolute value of -3 times 6 is the absolute value of -18, which is 18. The absolute value of 2 minus 6 is the absolute value of -4, which is 4. And the absolute value of 5 plus 2 is the absolute value of 7, which is 7. Let's try one more example that requires a few steps. We need to find the absolute value of -13/10 plus 4/5. First, we need to perform the operation inside the absolute value bars. We find a common denominator, which is 10. So we have -13/10 plus 8/10. This simplifies to -5/10. The absolute value of -5/10 is +5/10, which can be simplified to 1/2. So the absolute value of our expression is 1/2. It's crucial to always perform the operation inside the bars first, before taking the absolute value. This is a common mistake to avoid. Let's quickly review what we've learned. We've covered 3 essential topics today. First, we defined irrational numbers as non-repeating and non-terminating decimals, and we saw how they fit into the broader set of real numbers. Second, we introduced inequalities, learning the symbols, and, grow, and how to represent their solutions for both real numbers and integers on a number line. Finally, we explored the concept of absolute value as the distance from 0 on a number line, and we practiced evaluating expressions that involve it. These concepts are fundamental building blocks for many areas of mathematics. You should now be able to confidently work with these ideas.